Let's start by talking about proteins. Proteins functionally do everything, like speeding up chemical reactions, sending signals between cells, and providing structural support. These proteins are made up of chains of amino acids that each contain R groups, which interact with each other to fold into 3D shapes. The 20 amino acids are separated into 4 groups based on the properties of their side chains: the 9 nonpolar uncharged, the 6 polar uncharged side chains at physiological pH, the 3 polar basic amino acids, and the 2 polar acidic amino acids. It's important to note that cysteine and tyrosine are considered slightly acidic because the side chains have ionizable groups with relatively high pKa values of 8 to 10, but not too high compared to serine and threonine with the pKa values of 16 to 18. Specifically for this video, we'll be talking about tyrosine. At the center is the alpha carbon, which is bonded to 4 different groups: an amino group, a carboxyl group, a hydrogen atom, and a side chain containing a phenyl ring, which includes a hydroxyl group that can act as a weak acid. This gives tyrosine 3 titratable protons, meaning it can donate protons at 3 different pKa values.
So what happens when you change the pH? Tyrosine's structure changes because the protonation states of its groups shift. Let's go from low to high pH and watch how the structure changes. At very low pH, around 1, all of the groups are fully protonated. The carboxyl group is COOH, the amino group is NH3+, the phenyl side chain is OH. At this point, the net charge is positive 1. As we raise the pH to about 2.2, the carboxyl group deprotonates to COO-. This gives us Zwitter ion, where there are equal positive and negative charges for a net charge of 0. Around a pH of 9.1, the amino group deprotonates to NH2, and the molecule has a net charge of -1. Finally, at a pH around 10.1, the phenyl group begins to lose its proton, becoming an O-. At high pH, tyrosine carries a net charge of -2. To recap, the key pKa values for tyrosine are a pKa1 of about 2.2 for the carboxyl group, a pKa2 of about 9.1 for the amino group, and a pKa3 of about 10.1 for the phenyl OH group on the side chain. As we look at the titration curve of tyrosine being titrated with a strong base like sodium hydroxide, we can identify 3 buffer regions and 3 equivalence points, each corresponding to the ionization of a different functional group. The x-axis shows the equivalence of base added, and the y-axis tracks the pH of the solution. Initially, at 0 equivalence, tyrosine exists in the fully protonated form tyrosine plus, with a protonated carboxyl group written as COOH, a protonated amino group written as NH3+, and a neutral phenyl side chain written as OH. The overall net charge here is +1. As we begin to add base, we move towards the first buffer region, centered around half an equivalent, where the carboxyl group starts to deprotonate. At this point, the pH is approximately 2.2, which is the pKa of the carboxyl group, and the system is buffering. Here, about half the carboxyl groups are deprotonated, and half remain protonated. The structure is a mix of fully protonated and Zwitter ionic forms. At 1.0 equivalent, we've added enough base to fully deprotonate the carboxyl group to COO-. The amino group remains protonated as NH3+, and the phenyl group still remains as OH. This gives us tyrosine 0, a Zwitter ion with no net charge, as we discussed before. As we continue titrating, we approach the second buffer region, around 1.5 equivalents, where the amino group begins to deprotonate. The pH here is close to 9.1, the pKa of the amino group. Once we reach 2.0 equivalents, the amino group is fully deprotonated to NH2, while the carboxyl remains as COO-, and the phenyl group is still neutral. At this point, tyrosine carries a net charge of -1, giving us tyrosine -1. Next, we enter the third buffer region at about 2.5 equivalents, where the phenyl side chain starts to deprotonate. The pKa here is approximately 10.1. Around this point, there is a mix of tyrosine with the neutral OH side chain and those that have lost the proton to become O-. Finally, at 3.0 equivalents, the the side chain is fully deprotonated. All ionizable groups have now lost their protons, and tyrosine exists in its fully deprotonated state, tyrosine -2, which has a net charge of -2. Between the first and second equivalence points, tyrosine has no net charge, as we discussed before. It is in its zwitterionic state. This is also the isoelectric point, or pi, calculated as the average of the pKa values of the carboxyl and amino groups. To calculate this, you would add 2.2 plus 9.1 and divide that quantity by 2 to obtain a pi value of 5.65.
Finally, to recap, tyrosine has 3 ionizable groups: the carboxyl group, the amino group, and the phenyl side chain with the hydroxyl group. Its structure changes with pH, which affects its overall charge, and its titration curve shows 3 distinct buffer regions corresponding to its 3 pKa values. Thank you for watching. We hope this helped you understand amino acids and titration curves a little better.